today we'll talk about chapter 11, electromagnetic properties. And we'll focus on the physical meaning of the electromagnetic properties in the soil media. So we've seen that from the theory, the electromagnetism theory, we see the magnetic permeability and permittivity and the electrical conductivity was the main property. And so three parameters are key. First is magnetic permeability, and this is a complex property, right? Because there could be some phase shift comparing to the external magnetic field change. So when you apply the alternating AC or the alternating magnetic field, then you have amplitude and the phase shift. So you can use the complex number. And the mu is the magnetic permeability, and mu naught is the magnetic permeability of free space, the vacuum. So in general, we use the mu rel, so relative magnetic permeability, which is normalized by the free space property, mu naught. Because the mu naught itself is very small number, so if you use the relative value, then it's easier to think comparing to the free space property. And permittivity is what? That indicates how the material can be polarized. Right? So epsilon is the permittivity, complex permittivity. And here the real value, the epsilon prime, captures the polarizability of media, and epsilon double prime is what? It's a loss term, right? So that implies the energy loss during the wave propagation. And here also we use the relative permittivity, that's divided by the epsilon naught. So this is the permittivity of free space. So kappa and epsilon, right? Kappa is the relative permittivity. And the last one is the conduction. So how the charge can move, how fast they can move, or how much quantity can move. Right? Conduction is related to the quantity of the charge moving, also the velocity of the charge moving. Okay? So sigma and the sigma effective. So when you apply the DC at the zero frequency, that's just the DC conductivity, and AC conductivity is when you apply the AC current. 쓸 게 많을 텐데 뒤에 있지 말고 앞으로 나와도 됩니다. 여기 퉁퉁 비었어. 쓸 게 많을 텐데. 오늘 필기할 게 많을 수도 있어요. 운동장에 있어. So I think I told you that this double prime, the kappa double prime, is in phase with the conduction. So when you normally measure the imaginary value of the permittivity, you also capture the conductivity together. Right? Okay, so we'll talk about the magnetic permeability first, and then we'll move on to conductivity. Then that will be all for today. Magnetic permeability. So moving charge generates the magnetic field. So when you have a moving charge at constant velocity or at time varying velocity, it generates the magnetic field. And the magnetization of the material is proportional to the intensity of the external magnetic field. Right? So if you apply the strong magnetic field, the material will be more magnetized. So it's like you have a strong magnet and you put it close to the material, then material will be magnetized. Right? And small magnet or the weak magnet, then it's going to be less magnetized. Right? So M is a magnetization. That's equivalent to polarization. And the magnetic induction is expressed with this magnetic permeability of the field and the H plus M. So then if you plug this equation here, you have final equation, this one, mu naught times 1 plus psi m. And here the psi is the magnetic susceptibility. And together, this can be captured in the mu, the magnetic permeability. So this psi m and the mu are the complex number. So you have amplitude and phase. And these values are also dependent on the frequency. So it's a frequency dependent complex quantity. And so mu rel, the relative magnetic permeability, mu rel star is prime, the mu prime minus j mu double prime. So real part captures the magnetizability, and the imaginary part captures the energy losses. So it's same with the permittivity. So partial, why we have a magnet? So the magnetic property or magnetization is because of the partial filling of an electron shell, and that's because of the unpaired electron. So you have in the orbiter, do you remember the orbiter, right? The 1s, 2s, 2p, 3s, 3p, 3d, something like that, right? And if you can feel the electron paired in here, right? And if you have an unpaired electron, then, electron, let's say that you have a hydrogen atom. This is a proton, and you have a 1s cloud. Right? And you have an orbital, and this is spinning. So if you imagine that the electron is moving at constant velocity, this is going to generate the magnetic field, right? So you have an electron moving like this, then this is the magnetic field generated by that, right? And also the electron itself can spin. So spinning electron will also generate the electric field. So electric field can be generated by the movement of the electron in the orbital, and also the spinning of the electron itself. So the magnetic property is determined by the interaction between the magnetic fields within the atom and the magnetic fields with the neighboring atoms, and tendency for magnetic dipoles to become aligned in response to an external magnetic field. And you have a counteraction, that's by the thermal agitation. So when you have a magnetic pole that can be all randomly aligned, then it's gonna compensate each other. So if you have this kind of a unpaired electron and that's all aligned, then this is magnetized. You can say that it's magnetized. But generally in the material, for example, in iron, it doesn't have the magnetic property, right? It doesn't attract any ferromagnetic material. So this has all randomly. The magnetic dipoles are randomly aligned, so they compensate each other. Right? So if you apply a very strong magnet at this iron, which is unmagnetized, then this magnetic dipole will align so that it becomes a magnet. So depending on the magnetic property, we can categorize the material into three categories: diamagnetic material, diamagnetism, or paramagnetism, and the ferromagnetism. And diamagnetism is, let me jump into this one first. So this is when you apply the magnetic field, it feels the repulsion. So material, for example, water, when you apply the magnetic field, they feel the repulsion. So the orbit of the electron is modified to oppose the change when a material is placed in a magnetic field. So material feels the repulsion from the magnetic source, and this creates a small negative susceptibility. So the psi is negative value, minus 10 to the negative 5. So it's gonna be like 1, 2, 3, 4, 5. Right? So the mu rel, the real value of the relative permeability will be 9.9999x. So that small value is the susceptibility and the magnetic permeability of the diamagnetic material. So here, copper and the kaolinite in the soil mineral, and the water is the diamagnetic material. So the orbit of the electron governs the magnetic property in this diamagnetic material, and the paramagnetic material is opposite. So when you apply the external field, then it induces the attraction force. So external field induces the magnetic dipole oriented parallel to the field, and it generates the attraction. So it has positive value of the magnetic susceptibility. So psi m here is around plus 10 to the negative 5. So that's going to be plus 0.1 or something. And the Montmorillonite is paramagnetic material. And the last one is the ferromagnetic material. So that the total magnetic moment is the summation of the spin and orbital moment, as I said, of the electron. And the atomic magnetic dipoles are closely aligned, providing a strong magnetic field. And alignment, this dipole alignment remains until the Curie temperature. So it becomes a paramagnetic after this temperature. Permanent dipole moments form the domains where the magnetic dipoles are aligned in the same direction. So the dipole moment in, for example, the iron, let's say that this is the iron, and dipole moments are, depending on the crystal structure, it could be aligned in some direction, then this will generate a magnetic dipole, right? So, but in unmagnetized state, the domain direction renders a medium with a zero net magnetization because the dipoles are aligned randomly. When the H external field is applied, the rotation of the spin within the domains or the movement of the domain won't occur, so then it becomes magnetized. So when you have just unmagnetized iron, you apply the strong magnetic field H, then the domain aligns and it becomes magnetized. So it can also have the remnant magnetic dipole. So if we compare the susceptibility value, here the diamagnetic material, the water, copper, silver, carbon, bismuth, that's around negative 10 to the minus 5. Right? And the paramagnetic material, sodium, aluminum, the liquid oxygen, 10 to the negative 3, so it's a positive value. negative value. And ferromagnetic material, when you look at it, it's 5 times 10 to the 3, so it's 5,000, right? And alloy, this is the one of the iron alloy with the nickel, and so you can see the order of magnitudes are really different. It has a very high magnetic susceptibility and also the magnetic permeability. So generally the magnetic survey captures and detects this ferromagnetic material. So it cannot distinguish between the diamagnetic and the paramagnetic because the differences are so small. Okay, then the magnetic permeability, when we look at the high frequency response and the low frequency response, the domain walls are unable to follow the external field. So at the high frequencies, so you're changing, alternating the external magnetic field, and the dipoles are to maybe have viscous drag, or the inertias are so big, too big to follow the external field change. So the only magnetization mechanism is spin rotation in domains. So this occurs there when you have a resonance. And at low frequency, movement of the domain walls manifest at a low frequency relaxation. So this is, for example, in a ferromagnetic material, you have one domain that has a magnetic dipole in this direction, and this has maybe it could be because of the crystal structure. Then this is another dipole. Then when you apply the magnetic field H, and this will change and this will change, and then they can align together with the external field, and that's where the relaxation occurs. So this manifests at the low frequency, and at high frequency, because it's changing too fast, they cannot move, so only the electron spin rotation affects the magnetization. So in the relaxation, damping effect is more significant than the inertial effect, and the resonance, the damping effect is less significant than the inertial effect. Inertial effect is more governing. Then the spectral ratio is like this one. So at the high frequency, you have a resonance around 10 gigahertz here, and the low frequency, you have a relaxation about 10 kilohertz. So when you have a relaxation, then this is, you have a decrease in the magnetic permeability, so in the real value, and the resonance, you have this kind of behavior, and you have a sharp peak in the lowest term. So I think this kind of a graph is familiar to you. So if you remember the Biot-Gassman equation, then you had the lower BP, right? BP 0 and the BP infinite with the frequency. And at the same time, the damping was like this, right? This was 1 over Q. And this is a typical behavior of the relaxation. So, and with respect to frequency. Okay. Then, so the magnetic permeability has a frequency-dependent behavior, and if you imagine that you have a mixture, for example, in the soil that's diamagnetic, and you have inclusion of the iron, and then what will be the relative magnetic permeability of this mixture. Right? This will be function of soil and their volume fraction, right? And for example, let's think about the density. Density is what? GS grain times 1 minus porosity plus rho every porosity. Right? So this is just a volumetric average, right? According to the volume fraction. And you can also derive some kind of a mixture equation or the equivalent relative magnetic permeability using this pure property and their volumetric fraction. It's called the mixture model or effective medium model. And this effective medium model are very useful to predict the property of the mixture. And you can use it for the permittivity model or magnetic permeability model or the stiffness model. The applications are very wide. So the homework here is to review the mixture model in the textbook for the ferromagnetic inclusion and find out the basics of the MRI, the magnetic resonance imaging, and the NMR, and basics and applications of the magnetic survey. That's just a quick homework. And when you look at the mixture theory, actually the geometry of this or the spatial distribution of the inclusions are important factor. So it could be aligned parallelly like this. This is the inclusion, or you may have a vertically aligned inclusion, right? And there are tons of it. So you can have a spreaded one or concentrated one, right? So depending on how they are included and the morphology of the inclusion inside, you may have a different result. So this homework will be useful to find it. Question so far? So then let's talk about the conductivity. And the electrical conductivity, sigma, is the measure of the charge mobility in response to an electric field. And it follows the Ohm's law. The current density J is equal to E times the sigma times the external field. So the sigma is, you can think of the quantity and I think the velocity. And the medium is conductive when the electrons can be easily removed from the outer valence shell of atom. So you can think of the metal. Right? In the metal, you have a free electron at the outer shell. These electrons are randomly moving within the medium, preserving the time average neutral electrolyte. So in the metal, even though you apply the current, that the metal will remain electrically neutral. Right? And if charges are not free to move, the medium is dielectric or insulator. And still, positive and negative charges displaced locally related to each other. So it tells you this is about the polarization. in the presence of an electric field rendering a polarized medium and a polarization current. And when we look at the aqueous electrolyte, so the DI water is not conductor. It doesn't conduct any current, right? But as soon as you add the salt, and the salt will be hydrated, and so you have ions that can move, so that the electrolyte, the water and the salt solution is now become the conductor, right? It's a conductive material. So the movement of the hydrated ion, for example, you apply the electric field, and this is the solution, and you have ion, and this will move, right, to a certain velocity, and when the velocity becomes a constant, then it means that the force is equilibrated, right? So what force is acting on this charge? Electric force, because of the Coulomb force, right? Coulombian force is attracting this charge, and the resisting force is what? Viscous drag. So the ion will have to swim against the water molecules, right? So you have a viscous drag, and the electric force is balanced. So the F, this is electric field, and the opposing viscous drag is equal. Sorry, do that. And this gives you the ion mobility U. So let's do it together here. So when you add the salt in the water, and this, for example, the potassium chloride is here. So when you add the potassium chloride to the water, and water will take apart this cation and the anion, and it's going to be hydrated. So the potassium ion will be hydrated by this water molecule, and also the chloride anion will be hydrated with the water molecule. And this will move together as a cluster. It's called the ion cluster, or the hydrated ion cluster. So when you think about the viscous drag, you cannot just think about, you can't consider only the single ion here. You have to think of all these ion cluster. The clusters are moving together in response to the electric field. So do you remember the sedimentation test? You have a particle going down in the water, and the dragging force is what? And the velocity is this one. Dragging force is 3 times area times velocity, right? So 3 pi d times velocity, something like this one. So that here the d will be the particle diameter, but in this case the ion cluster, the diameter of the ion cluster will be the d, not just only the potassium. And the electric conductivity of the electrolyte. So this is the conductivity of the electrolyte. Electrolyte means that the salt solution or the saline water, and the quantity, also the mobility affects the electric conductivity. So if you have a more hydrated ion, then the conductivity will increase. Okay? That's going to be proportional to the concentration of the ion concentration. And if the ion can move fast, then you have higher conductivity. And also if your ion have higher valence, like the calcium has the 2+, and the sodium will have 1+. So if the calcium move at the same rate, with the sodium, then the conductivity will be double of the sodium. So their balance will affect their electrolyte. So number of the hydrated ion and the ion mobility and their balance. So here this can be calculated from the molar concentration, and if we know the ions inside, then this can be also identified, and we need to derive the ion mobility. Here is the equation that I just told you before with the previous slide, and the F, this is the electric force acting on the hydrated ion. So this is the Q, the charge, and the electric field, force E. And for one ion, if the balance is Z times the charge of the electron, E naught. So the dragging force against the movement of the charge is 3 times pi d times v, and the viscosity. Oh, yes. So previously I missed the viscosity part. And the d is the hydraulic diameter. And if we replace the diameter with the radius, then this becomes the 6 pi v r and mu, the viscosity. So then at the terminal velocity, when the charge is moving at constant velocity, the force is balanced. These two forces are balanced. So the Z E naught times E equals to 6 pi v r mu. And we can define the ion mobility as the velocity per unit electric field. So then the U is the ion mobility, and that's the velocity divided by the electric field. Then the final equation will be like this one. So the units are velocity is meter per second, and the electric field is what? Potential divided by the distance. So the V over meter. So meter square V S. So you can calculate the ion mobility using this equation, and when you look at the equation closely, you have a radius at the denominator. Oh, is it denominator? Yeah. So the larger radius will have a slower velocity. Right? Mobility will be less low, and mu, also the higher, the more viscous liquid will result in less mobility, and higher valence will result in the faster mobility. Okay, so for the aqueous electrolyte, you can calculate the conductivity of any salt solution using this equation. So here, for an ith ion, so for a given ion, if you know the molar concentration and the balance and the ion mobility, and this is the Faraday constant, F. Faraday constant, then you can calculate the electric conductivity of the electrolyte, theoretically. For monoion electrolyte, so C is the molar concentration of that ion. For example, maybe like you can say the sodium ion, and the molar concentration of that, and the balance will be 1, and we know the radius, hydrated radius, and the Faraday constant is known, so you can calculate the electrolyte conductivity. But these equations are valid for only a low concentration, where the ion and ion interactions are negligible. So they are each very dilute, so the ion cannot collide, or they don't affect the other ions' movement. Right? So, but that means that if you add more salt, then this the electrolyte concentration. So at the low concentration, this will be linear. Right? At some point, when the concentration is too much, then there are too many ions are moving together, so that they will affect, so the increment will be less than that. Right? At the higher concentration, the decrease in mobility may prevail over the increase in ion availability, so the conductivity may decrease. So at sometimes you may have a decrease in electric conductivity too. Okay? So this equation is valid when you have a low concentration here. So linear region only. Question? Okay, and then now you have a soil and filled with pore fluid, and pore fluid can be DI water, or could be electrolyte. So it could be saline water or the brine. We call it brine when it has a salt, right? So the electric conductivity of the soil is a function of what? Soil's electric conductivity and pore fluid electric conductivity. Right? It's like you can think of the bulk modulus of the soil mass with the soil skeleton and the pore fluid. It's going to be the same. So in the mixture model, let's start with the low specific surface soil. So for example, it's the sand or the silt. So the particle itself is not conductive. So the mixture conductivity depends on the orientation of the layers with respect to the direction of the applied field. And here you have a series model and a parallel model. Why don't you guys derive the sigma mix? If this one has the sigma 1 and sigma 2, and also this is sigma 1 and sigma 2. 유도해 보십시오. Derive electric conductivity of the mixture for the series model and the parallel model. And D1, D2 is the thickness of the media. So material 1 has the thickness of the D1, and material 2 has the thickness of D2. Here, in the series model, the current going through this material 1 is the same with the material 2, right? So current I1 is I2 is the total current. And what about here? The I is splitted. So you have a I1 and I2, and the sum of this I1 and I2 are the same with the I, right? So that's the main carbon equation to derive it. 오케이. 구한 사람. 시리즈 모델부터 얘기해 볼래? 원 오버 시그마 믹스처는 이렇게 되는 거죠. So if you convert it to resistivity, then raw mix will be D1 plus D2 times rho 1, D2 D1 plus D2 times rho 2. Okay? Same for the series. And for the parallel, sigma m is so it's just the weighted average, right? So I think it's correct. Oh, here the D1, D2 is already, I think the D1 plus D2 is 1. It's a ratio. So if you think about the porosity, D1 could be a porosity n, and D2 could be 1 minus n, right? And for the series model, voltage drop or the potential drop from here to here is the same with the delta V, and you have a V1, that's a drop 1 at the material 1, and V2 is the another drop 1 drop, right, at the material 2. So potential drop V1 is the current times the resistance, and current time resistance, and that's the current time the equivalent resistance. From that you can derive this equation. And here you have same voltages applied to material 1 and 2, but the current are splitted, so the summation of the I1 plus I2 is the I, total I. So from that you can derive this final equation here. So this one and this one. Sorry about the mess at the right side. Only write down the equation in the left side. Okay, so using this concept, we can model or we can predict the conductivity of the soil mixture when the soil has a solid particle and a pore fluid. Okay? So if you know the particles electric conductivity and if you know the pore fluid electric conductivity, using this kind of a two model, we can kind of predict the upper and the lower bound of the mixture conductivity. And what about the high specific surface soil? Before we go into that, I would like to review some clay mineralogy. So I adopted some slides from the soil mechanics here. Clay consists of the basic unit. So if it's a one-to-one mineral, it has a tetrahedral and the octahedral, right? And in the octahedral, you have various cation. It could be calcium or aluminum or magnesium, right? And depending on the manner of how they stack, you have a different clay mineralogy. So if you have a one-to-one mineral, it could be a kaolinite. If you have a two-to-one mineral, so you have a one tetrahedral shade, one octahedral shade, and the other tetrahedral shade, then it could be a Molar-Montmorillonite. So these are the typical clay mineral that we encounter in the field. So this is a kaolinite, this is a one-to-one. You have a one basic unit and the other basic unit. And halloysite, another one-to-one, but you have a water. And Smectite is a two-to-one, so it's a general name for the Molar-Montmorillonite. And electrolyte, you have a potassium that have an ion bonding between two units. And chloride, you have a different also the layer between the two units. So, and this is a basic, it's called, this is the basic unit. Right? And when you look at the kaolinite, you have a octahedral sheet and a tetrahedral sheet, and there's some interlayer and another octahedral sheet and the tetrahedral sheet. Okay? And between this basic unit, the bondings are hydrogen bonding. The hydrogen bonding are very strong, so that when you add the water cannot penetrate inside. Okay? They have very strong bind. So you don't have swelling, interlayer swelling. And the width and thickness is around, the width is 4 micron, thickness is like tenth of it in general. When we look at the SCM picture, this is a picture of the kaolinite. And people mistake that the layer here is the interlayer here, but it's not. Right? So when you look at this, the interlayer, the thickness of each layer is, how much is it? Less than 1 nanometer. Right? And here, this is 17 micrometer. So this is 17 micrometer. So this will be around, if we divide it by the 20, then this is around 1 micron. And itself, this one is 0.5 micron around. Right? So each plate will have a stack of the basic unit. Right? So inside here you have a hydrogen bonding between the basic units. So if you imagine the clay mineral and this goes to infinite, to the horizontal direction, and the stack, this stack goes to around 0.5 micrometer, and that determines the thickness of the clay particle. Okay? And the other example is the Molar-Montmorillonite, and here you see that this is around 1 micron, and also this goes to infinite. And here, between this tetrahedral and tetrahedral sheet,
you have van der Waals interaction only. So it doesn't have the hydrogen bonding. So van der Waals attraction is weaker than the hydrogen bonding, so the water can penetrate between this interlayer. So that's why you have a swelling in the Montmorillonite. And also this has the many charge deficiency. When you look at the SEM picture, scanning electron microscope pictures, you see that the much smaller than kaolinite. And how much would that be, this thickness? 10 of nanometer, maybe. I think 3 nanometer is too small, so this will be much larger than that. I think 10 of nanometer. This will be 10 of nanometer. So still, that when you see this one is a stack of this basic units. Okay? You cannot. So far, we don't have the technology to look at the interlayer between the Montmorillonite. So when we think about the clay, you have an interlayer. So this is the one particle. Actually, you may have a layer of that. Sorry, this will be one particle, a stack of it, and actually the width will be much larger than that. And you have an interparticle space. It's called the pore space. This is the pore space, or the void. And another particle here. And also you have the interlayer and a stack of the basic units. Okay? So the macropore, so in general, when we say the pore or the void in the clay, we are indicating these interparticle spaces. Okay. And in clay, when you add the water, you develop the absorbed water layer, right? Or we call it diffuse double layer. And that's because of the negative charge in the clay surfaces. So clay itself is negative charge. So it's electrically, it's not neutral. The balance is actually broken. So you have to have a cation to balance it. So when you have a dry clay, you always have a cation observed on the clay particles. Right? So this is electrically neutralized clay particle. Clay particle itself will have the negative charge. And because of the negative charge, it has a cation, and when you add the water, this cation will be hydrated, and there's some layer, that the water layer, that is kind of structured. So it has a different characteristic from the free water. So cation concentration will decrease as you go further away from the surface of the clay mineral. And when the potential, zeta potential of this electric field decreases to 1 over E, that's we define is the thickness of the double layer. Right? And the thickness of double layer can be calculated using this equation. So this is the double layer thickness. And when you look at this one is the permittivity in vacuum, and K, the kappa is the relative permittivity of electrolyte or the pore water, and K is the Boltzmann constant, T is the temperature, N is the cation concentration, and B is the balance. So if you have the electrolyte, more concentrated electrolyte, what will happen to the double layer thickness? Double layer thickness will be thicker or the thinner. Thickness will decrease, right? So you have more cation to compensate the negative charge on the clay surfaces. So clay surfaces have static charges and you have to balance it anyway. And if the electrolyte have more cations or the anion, then with the small thickness, they can compensate these negative charges. Right? So thickness will be less than that, less than the DI water. So the DI water, in case that you have the largest, the double layer thickness. Right? And you can compare with the sodium ion and the calcium ion. Right? Calcium ion have 2 plus, and sodium is 1 plus. So for the same amount of the concentration, calcium will develop the thinner double layer thickness because they can compensate the negative charge more effectively, right? So the double layer thickness is a function of the pore chemistry, pore chemistry, or the ion concentration and the ion type in the electrolyte. So here is a more detailed schematic. So you have a dry clay, and when you add the water, and this water will hydrate these cations, right? And you may have a precipitated salt. So then this water will be stuck. So there's a 1-2 monolayers. That's very strongly observed on the surfaces. And you have a double layer. There's relatively the ion can move a little bit. And there's a far field in the free water. Then there's a just electrolyte. The ions are moving freely. Okay? So as you go further away from the clay surfaces, you have a stone layer that's strongly binded and a little bit structured is the double layer, and you have a free water. Okay? And it's difficult to remove this stone layer. So always when we measure the potential, we cannot measure at the surface. We only measure here at the stone layer because it's hard to remove these materials. So this is the stone layer potential, and when the stone layer potential decreases to 1 over E, then this is the double layer thickness. Right? Diffuse double layer. So using this kind of a concept, we're gonna correlate to the electrical conduction in the clay mineral. Before that, okay, specific surface area. Okay, so what's the definition of the specific surface area? The area of the particle divided by the total volume, or area of the particle divided by the total mass, right? You can have the area over mass or the area over volume. So in here, we're using this second definition, the area over the mass. So then, what will be the unit? Unit will be like meter square per kilogram or meter square per gram, right? So one example, why don't you guys calculate this specific surface area for 2 cubes? The first one is 1 centimeter at each side, and the other one is 1 micrometer at each side. 2.26 centimeter per square per gram. Centimeter per square gram, so then if you convert it to meter square, then there will be 10 to the negative 4, right? So here the area will be 6 times 1 centimeter square, right? So you have a 6 size, and the volume will be 1 cubic centimeter, and if you multiply the density, then you can get the mass, right? So the area divided by the mass will give you this value, 2.3 times 10 to the negative 4 meter square per gram. What will be the second one? .26 meters square per gram. Okay. So it's the same shape, and the size is only different. So you have a 1 centimeter size, and this is the 1 micrometer. Right? So you can see that the specific surface area is inversely proportional to the particle size. So as you have smaller particle, you have larger specific surface area. Okay? So, for example, the silt, and comparing to the clay, the silt has larger particle size than the clay, so the silt will have the smaller specific surface area than the clay. Then among the clay mineral, if you compare the Montmorillonite and the Kaolinite, Kaolinite is larger than the Montmorillonite, so the Montmorillonite will have the larger specific surface area. And that's also correlated to the liquid limit. Liquid limit, the Montmorillonite's liquid limit is larger than the Kaolinite because of the higher specific surface area. So the typical values for each clay mineral, the Montmorillonite is around hundreds of it, so hundreds, or if you include the interlayer surfaces, then it becomes the 700 square meter per gram, and electrolyte is around 60 to 100 meters square per gram, and the Kaolinite is the least one. We don't have time, so let's skip it. This one too. Okay. So, high specific surface soil, when you have dry soil, you have a counter cation that balances the negative charge on the clay surfaces, and you may have also the excess salt that's precipitated during dry. When you add the pure water, this cation will be hydrated like this, and it's going to form the double layer. And also the excess salt will be hydrated, and the pure water will become the electrolyte. So the overall, the conductivity, electrical conductivity of the soil mixture will be larger than 0, so that the soil becomes the conductive material. So then what happens if you compress it? So you are squeezing the pure water out from the soil. So during the compression, the porosity will decrease. Then the electrolyte, the volume of the electrolyte will decrease. Right? So the soil particle will get squeezed, and the pore spaces decreases, and the water will squeeze out. So then, as your porosity decreases, the conductivity also decreases, because you are taking out the electrolyte. So electrolyte is, in this case, is the main channel for current to flow, or any charges to flow. And when you have the dry soil with no excess salt, what happens? When you add the water, this is also when you add the water, pure water, we can think of the two cases. You have a suspension and you have soil, and in the suspension, the particles are not touching each other, so that you can idealize with the one particle. And when we apply the electric field, the double layer will deform locally, so it's going to be polarized. But still, you don't have any particle that's connecting each other to the other electrode, so the charge cannot flow. But in the soil, you have many particles that touching each other, so that even though when it's polarized by the external electric field, then this charge can jump to the diffuse layer, and by that the electron can move, so that this is called a surface conduction. So the charge can move from one diffuse layer to other diffuse layer, and from that the electrical current can flow. Okay. And this diffuse layer will be formed on the surface of the clay, so we call it surface conduction. Actually, in this case, you don't have so in the water, you don't have any free charge. Right? So as you compress the soil, porosity decreases, so that the distance between particle will decrease, so the charge can move more efficiently, so the electrical conductivity will increase. Actually, this is very idealized case, but this case is when the surface conduction is governing over the electrolyte conductivity. Then, I think we have, so this is the explanation about the surface conduction. So mobility of the ions in stern layer is limited. So you have only the ion mobility in diffuse layer. So ions in counter ion clouds near particle surface contributes to the surface conduction. And this as the sigma. So when you have a clean sand, if you add the DI water and if you measure the electrical conductivity, it's almost zero, because the clean sand means that it doesn't have the excess salt, and the sand itself is not conductive material, it's a dielectric material. You have a clean clay material. When you add the DI water, it still conduct. It could be conductive because of the surface conduction. So high species surface soil and the low species surface is the difference of that. Whether it develops the double layer or not. Surface conduction can be also estimated using the zeta potential, and here we use the lambda. So the lambda is the surface conduction by the diffuse double layer, and the sigma is the surface charge density, the rho s, and u cat is the cation mobility, and using this we can calculate the surface conduction theoretically. So then when you have an electrolyte in the clay, so then you have a clay particle, and if you apply the electric field, then you have also the electrolyte as a pore fluid. So you have many cation and the anions that can move, right? And you have a surface conduction that contributes the sigma. So then this can be idealized to the parallel series, right? The parallel model. You have lambda and the sigma electrolyte. Right? And that's this diagram. So if we can estimate or derive the equation for sigma mixture, so mixture's conductivity, that's gonna be a function of what? The surface conduction of this clay material and the sigma electrolyte. Right? So you have sigma in the parallel series, the volumetric fraction times the electric conductivity. Right? The sum of that is the total mixture conductivity. So electrolyte times the thickness of the water. The thickness of water is this one. So you can imagine that these clay particles are repetitively, periodically repeat. So from here to this one is the one basic unit. And thickness of the water is the TW from here to here, and the thickness of the particle is the TP. And then sigma electrolyte times the TW plus sigma P times TP. So this is the particle's conductivity. And you have a surface conduction, 2 times lambda DDL, right? Because you have two surfaces, up and down, and divided by the total height, or the total thickness. And then here the water thickness is much larger than double layer thickness, and this is the assumption. And the porosity can be expressed with the TW, and the water thickness and the total thickness, right? TW over T total is the porosity, and the particle thickness over the total thickness is the 1 over n, 1 minus n, 1 minus porosity. So then this will be simplified to the second equation. Porosity times the electrolyte conductivity, 1 minus n times the particle conductivity, and the surface conduction times 1 minus n. You have this one, right? Thickness of the particle. And I want to remove this one because it's difficult to estimate the particle thickness, right? Instead of that, it's easier to use the surface area of the particle. So then, using the correlation or the definition, according to the definition of the specific surface area, area of the mass is the 2a over thickness, area, and lambda p, rho p is the particle density. So the 2 over Tp will be specific surface area times the density, particle density. So this goes to here, and the final equation can be expressed as follows. So the first term is the contribution by the electrolyte, and second term is the contribution by the particle itself, right? Sigma p. Generally, the sigma p is close to 0 because it's a very small number, and you have the last part that's contribution by the surface conduction. So here the gamma is the unit weight. Unit weight, particles unit weight over the g is the same with the density. So this assumes the series or parallel alignment. Parallel. It assumes the parallel alignment of the constituents. So parallel to electric field. Okay. I think this is the same with the previous equation. So when the particle conductivity is very low, so sigma p is much less than the electrolyte conductivity, then you can ignore the second term, right? This one. Oh, there's now the first term, this one. So then the particle, the mixture's conductivity can be simplified to the following: the function of the electrolyte conductivity and the surface conduction. When the large particle with very small surface area, so this is the case for sand or silt. If the specific surface area is very small, then this term is relatively small comparing to the first term. So this governs the mixture conductivity. So this goes to 0, so that the mixture's conductivity is just a function of the porosity times the electrolyte conductivity. Actually, this is the same with the Archie's law. And we're going to learn about that soon. So Archie's law is very effective for the sandstone and the non-conductive soil, very coarse soil. Here, this shows the is to get some idea about the contribution by the surface conduction. So, when the mixture conductivity is the same with the electrolyte conductivity, then you can expand it with this one. And when you manipulate the equation, you come up with this equation. So, if this value, the last one, the lambda times S times rho over electrolyte conductivity is larger than 1, then it's this area, surface conduction. And if it's less than 1, that's this area, the control by the electrolyte conductivity. And this is the low scale, so DI water electrolyte conductivity is 10 to the negative 6, fresh water 10 to the 3, 10 to the minus 3, and sea water is about 1. And here as the specific, so this is the sand case, and this is around here. So you can see that for the fresh water and the sea water in the field, generally the electric conductivity of the sand is controlled by the pore water's electric conductivity. For the clay, this is the case when the specificity is very low and high, and in some area the surface conduction governs the overall conductivity, especially in the fresh water. But when you have very salty water, then still the electric conductivity of the electrolyte governs the clay soil's the conductivity. So you can think of the pore waters one or the surface conduction, which one is bigger, okay? And which one will be more dominant for determining the mixture's conductivity. Okay, good question. So we've seen the electric conductivity of the soil media and the magnetic permeability. And next class we'll talk about the permittivity of the soil. Then we're done with the chapter 11.